All right, hi BC Calculus. This is my section G class. Okay, we're going to cover two topics today. One, I'm going to give you a shortcut for limits to infinity of rational functions. And then we're going to talk about limits to infinity of non-rational functions and what you do in situations like that. And then we're going to go over, work through some exercises, okay? What I don't have at home with me, I think actually never mind. Let's just listen. Okay, so the first thing to note is to figure out what a rational function is. Okay, all of the expressions on the left hand side are examples of rational expressions. A rational expression is a polynomial over a polynomial. A polynomial has terms that are raised to degrees of x that are integers or constants, okay? So the power of x, if it appears in a polynomial, is going to be an integer, 1 or greater. Of course, you can have constants as well. Technically, those are 3x to the 0, right? But we just call these constants. So this is a rational function. This is a rational function. The degree of the numerator for this rational function is 1. The highest power of the x in the polynomial in the numerator is a power of 1. The degree of the denominator is a power of 3. This polynomial right here has a degree of 7, degree of 2. You get my point, okay? These are all examples of rational functions. It's important to note that these are all not rational functions. The problem here is that the degrees are negative and non-integral, okay? Sinusoidal functions cannot appear in a rational function. There should be no square roots. So once you know what a rational function is, there's a lovely shortcut that you can always adopt with limits to infinity of rational functions. Please understand these are for limits to infinity of rational functions, okay? So now I'm going to go over here and do this. So here is the shortcut that I promised I would show you after our day one. If you're taking a limit to positive infinity or a limit to negative infinity of a rational function, if the degree of the denominator is bigger than the degree of the numerator, as it is in this case, this limit will always equal 0. Okay? Similarly here, let's take a look at the limit as x approaches negative infinity. The same thing. A limit to positive or negative infinity, if the degree of the denominator is bigger than the degree of the numerator, this is going to equal 0. I'm going to go and insert one over here. Let's take a rational function where the degree of the numerator is bigger than that of the denominator. So 4x to the 5th minus 3x squared plus 2 all over 2x cubed plus 5x minus 100, for example. Okay? Again, what you did night one was you kind of did this whole dominant terms thing, right? But if you have a rational function, and now we know what this is, we have this shortcut here. Here's a second shortcut. If the degree of the numerator is bigger than the degree of the denominator, this limit is always going to equal positive infinity or negative infinity, or does not exist. Okay? One more time. If the degree up high is bigger than the degree down low, this limit is always going to be non-existent. It's just a matter of positive or negative infinity. Let's take a look at another example. Limit as x approaches negative infinity of, let's do this, 4x cubed minus 3x plus 6, all divided by x squared plus 11. Okay? In this case here, the degree of the numerator is bigger than that of the denominator. You know the limit is not going to exist. It's just a matter of what kind of not existing, positive or negative infinity. And like I said before, when you've got a limit to negative infinity, sometimes you may have to do some thinking, right? If you think about this, right, the dominant term up high is going to be approaching negative infinity because x is being cubed. Dominant term down low is going to be approaching positive infinity because of this even degree. So this limit is going to not exist, but it's going to be non-existent negative infinity. All right? So 2 shortcuts with limits to infinity of rational functions. And here's your last one. if I have a limit to infinity of a rational function where the degree of the numerator is the same as the denominator, this limit is always going to equal the quotient, or, sorry, I just lost my pointer. It's always going to equal the quotient of lead coefficients. This is going to equal negative 6/11. Okay, another one, for example, is this one right here. Limit as x approaches positive infinity of 2x to the fourth minus 14 all over 8x to the fourth minus 2000x cubed, right? Degree of the numerator and denominator is the same. At the end of the day, this limit is going to equal 1/4, 2/8, which is 1/4. All right, so here you have your first limit shortcut. What I'd like you to do right now is to go swing over here to this page. And right now, would you please either, pause me, certainly. You certainly can pause me, but go ahead and do these. Oops, sorry. I want to include 22. Go over here and go ahead and do those evens. And I'm going to be quiet as I write the answers down. Okay? Use that shortcut because all of these here are indeed rational functions. I keep leaving 22 out of it. All right, go right ahead and I'll meet you at the end where you can work with me here. All right, there we have it. Well done. Well done. Now I want you to go back to your notes here, this other packet. We're going to talk about something else. There are two things I want to cover with you all, which is right over here. Okay? Actually, you know what? Let's try and get some of your homework done. I think this is the next page. Here we go. All right? So now let's talk about these limits here. We're going to have a conversation about what it means to have an indeterminate limit. All right, this page is a better kind of explanation of indeterminate limits than the first page. This this is from this packet, everyone. This is from the 1.1 to 1.3 packet. Okay. All right. So over here, computing limits. Let's go over here now. Take a look at question number 1 with me. This is a limit as x approaches 3. This is a rational function, but again, don't forget, okay, this is not a limit to infinity, so I can't use those shortcuts we just talked about. The limit as x approaches 3 of x squared minus 9 over x minus 3. The first thing we do, everybody, is we just plug in the value of x. We get 0 over 0. We're going to stop right here, okay? This is called an indeterminate limiting form. 0 over 0 is an indeterminate limiting form. In BC calculus, there are 6 different indeterminate forms. Wes and Wilson and Gigi, you guys covered 2 of them in AB. In BC, there are 6 of them. Here is your first indeterminate limiting form. When you have an indeterminate limiting form, what that means is you cannot tell by this what this limit is going to be. An indeterminate limiting form could, in the end up not existing, and it also could, in the end, existing. Indeterminate means that at this point right here, when you've done the plugging in, you can't determine what is happening. And the question you all probably have is, okay, how does one go about determining an indeterminate limiting form? We are not going to talk about L'Hopital's rule because we're doing chapter 1 thoroughly. So what do you do, right? Step 1 is, what we do is we try to algebraically manipulate the argument of the limit. Okay, so in this case, maybe some of you see it already. I'm looking at that argument and I can rewrite this way. This is the limit as x approaches 3 of x plus 3 times x minus 3 all over x minus 3. And I notice that when I make this rewrite, when I do this manipulation, I have a simplification. When we do an algebraic manipulation, you always want to then clean it. Here's me cleaning. And once you've cleaned, you try the limit again. Now let's try. It turns out this limit does exist. It equals 6. Okay? Let's come down here to these right here. Let's do this one right here. Okay? I'll meet you. I'll just do it together with you. The first thing we're going to do is we're going to plug in -1. Okay? You can't assume this is going to be indeterminate. You have to show that the form is indeterminate. Because once you show this is going to justify the step that you take next, which is that of trying to massage this limit. Okay? So this becomes the limit as x approaches -1. Up high, I get x minus 3. Oh, no, that's not right. X minus 6, x plus 1. X minus 6 times x plus 1. Down low, I get x minus 4 times x plus 1. That's my attempt. And notice, these cancel. And I'm left with, okay, the limit as x approaches -1 of x minus 6 all over x minus 4. Now I'm going to take the limit again. And it turns out I'm going to get -7 over -5 or 7/5. This limit ended up existing. All right? These two are going to involve factoring by grouping up top and then factoring a difference of cubes. I have a strong sense that you have forgotten those factoring patterns, so I'd rather than focusing on them here, I'll show them to you in class. I just want you to practice the calculus for right now. I do want to bring your attention to, let's take a look at these two, I think number 2 and number 3. So right over here, all right? Let's take a look at number 3 first, right here. Ready? Limit as x approaches 1. I'm going to plug in x equals 1. I get 0 all over 2. Oh, lucky us. It's just equals 0. That limit existed. No algebraic massaging necessary. Let's go up here now. Plug in x equals 1. We get 0 over 0. This is indeterminate. We always have to show the reader that we recognize an indeterminate limit. All right? I want to show you a trick with radicals. So I think you can tell here that in the case of indeterminate limits, when you have a rational function, an algebraic manipulation to try is the factoring method, right? If you've got a radical expression, this algebraic trick works, maybe half the time. So we're going to try it, okay? I have to erase this just to be able to show you the work here. But what we're going to do is we're going to multiply the numerator and the denominator by the conjugate of the radical expression. The conjugate means, right, this is something minus something. The conjugate of a minus b is a plus b. And what I'm doing here is multiplying the argument by 1. So I'm not substantively changing this argument. When I make this multiplication, okay, down low, I'm going to get this. I'm going to blow this up so I can squeeze my room in here. This is going to equal the limit as x approaches 1 of x minus 1 times root x plus 1 all over, if I multiply this out, everybody, I get x minus 1. Look at that. And then I notice I can do some cleaning. The cleaning is right here. And then my cleaned limit becomes the limit as x approaches 1 of root x plus 1. And this all equals 2. The limit exists at the end of the day. All right? Here's what I would like you to do, please. On the back of the limits and continuity test, on the back of the limits and continuity test packet, you will see the back side has limits of rational functions, and it also has limits that are potentially indeterminate. I've also included the answer key with it, all right? So what I want you to do now is go ahead and proceed with the homework. The screencast is now over. I hope this was very helpful, and I will see you all on Monday. Have a great weekend.